Step 2 is what? Step 1 is formulate the hypotheses. Step 2 should always be check our conditions. Our conditions for the single proportion case were that you have true p's out there, that you have a representative sample, preferably a random sample, and that you would have a sufficiently large sample, large being n times p and n times 1 minus p. What are we going to do in this case? We've got an additional condition. We have to make sure that these are independent samples. So you should have independent random samples. You also need both N1, P1, and also N2. Actually, this probably should be hats in here. Now I need to take a look. Now, I'll check it later. I think your textbook uses this form right here. I've occasionally used a slightly different one where I take into account what's going on in here, but we'll get to that. And if it's important, I'll bring it in later. So our conditions are this. Those would essentially be the same conditions I'd have for this confidence interval, wouldn't it? So for this confidence interval to be valid, I would want these same conditions to hold for that confidence interval. Step 3, here, conditions, and we have N1, P1 hat, N2, 1 minus P1 hat, N1, N2, P2 hat, N2, 1 minus P2 hat. Now, if we take a look at step 3, we have to calculate a z-statistic. It's going to be equal to an estimate minus the null value divided by the standard error at the null. Estimate is simply going to be P1 hat minus P2 hat minus 0. And you're going to have a big thing underneath the square root here. What should I put for this standard error at the null? Remember, in the case of a single proportion, when we got to the standard error at the null, what we did is we replaced the values of p with the null value. And that was because the null hypothesis was that the proportion in the population was equal to that null value. Can I put the true values of P1 and P2 in from the population into that standard deviation formula here? Does this null hypothesis tell me what the value of P1 and P2 is? All it tells me is that they're equal. All I know is that those two things are equal. I know nothing else. So in order to put a standard error down here, I could conceivably use this, but there's a better standard error to use. The better standard error is to go back to this situation here and look at this. And if that null hypothesis is true, that says that P1 is exactly the same as P2, right? So if P1 and P2 are exactly the same proportions, is there any reason to look at this population as two separate populations? No. So what I'm going to do is I'm going to merge these back together again to calculate a value of P hat that I'm going to use in my standard error. It essentially takes this sample and merges it back together again. To do that, I create the value of P hat, which is equal to N1 P1 hat plus N2 P2 hat all over N1 plus N2. Okay? And if you want to think about it a whole lot easier, think of it as nothing more than, instead of looking at this as two separate groups, I simply have one N, which is everything here, and I have a certain number that are in the category, which is the sum of these two, divided by that total N. That's all this thing is calculated. And from my experience, it's more often that you can easily calculate the P hat ignoring group 1 and group 2 than to simply calculate these individually. So now calculating P hat. If I put P hat in place of P1 and P2, now remember P1 equals P2, so P hat is my best guess at the common value. So I'm going to put a P hat into each of these. These two become the same value. So this is P hat 1 minus P hat over N1 plus P hat 1 minus P hat over N2. So what I end up with is P hat times 1 minus P hat all times 1 over N1 plus 1 over N2. Again, it's a little bit more complex. There's just a little bit more to it. The one tricky thing that we've got here is messing around with this P hat thing that didn't have anything similar to it when we were dealing with one proportion. But everything else here is pretty much the same. And in fact, from this point on, step number 4, the same as for single. And step 5, which is simply stating context, is again the same as it is for single proportion. It's always going to be the same stating context. So minor variation in setting up our hypotheses. A little bit more complex for determining whether we have sufficient sample size. We also have to make sure we have independent groups. Our calculation for Z is a little bit more complex, but not too bad. And then everything else from here on out is identical to what it was for single proportion. So look values up in table 8I1 and so forth, all the same.
What if they're not the same?
If we can reject the null hypothesis, that means this was a bad estimate for P. But the assumption here is always based on that being true. So we do all of our calculations based on the truth of that assumption. If they're not true, if that assumption is not true, then this will in fact be a bad estimate for P hat. But the end result will be a Z, which will cause us to reject the null hypothesis.
So basically we'll go through the equation up to that point and realize that we messed up and then have to start over again?
No, you don't have to start over again. At that point, what you've done is that you've gone through these equations and you've been able to reject this null hypothesis. You now know that P1 minus P2 has some relationship that is either not equals, less than, or greater than. So now you can take that and that is your conclusion.